Okay, so lecture 24, elemental analysis and determining empirical formulas. Two things. One is these are fairly complex problems that we have to do here, so if it's a minor mistake that I make along the line, if I don't catch it, I'll just put an addendum lecture. I've talked about this before, I haven't had to do it yet. Second thing is the cat's in the room, so cat's tail might be coming across here. Hopefully not. Alright, so empirical formula, or simplest formula, you should know that definition. When a 1 gram sample of an organic compound is analyzed by the combustion method, it produces 1.5 grams of carbon dioxide and 0.41 grams of water. What are the mass percentages of carbon, hydrogen, and oxygen? Okay, so this is talked about in your book, so we're going to assume that you have the basic idea of what's going on here, but we're going to, this organic compound contains carbon, hydrogen, and maybe oxygen. The carbon we're going to find by the CO2, from the CO2, the hydrogen from the water. And then once we know the masses of carbon and hydrogen, since we know the original mass of the sample, we can subtract the mass of the carbon and the hydrogen off and find the mass of the oxygen. So if what I said there has no meaning to you whatsoever, you want to go back to the book, back to your notes. And but otherwise, let's just go through it here. So we have 1.5 grams of CO2. And though I know I'm talking fast, I'm going to keep repeating myself and why we're doing the things we're doing here. So carbon dioxide, the organic compound was burned, and it changed from the organic compound to CO2 and water. So the organic compound contained carbon. The only carbon as a product is CO2. So all the carbon from the organic compound came from the CO2. But the mass of the CO2 has the extra mass of the oxygen, so we have to get rid of that. So what we do is carbon dioxide is 44 grams per mole of CO2. For every mole of CO2, there's 1 mole of carbon, and 1 mole of carbon is 12 grams. So what this has allowed us to do is find the mass of carbon that was in the CO2, because the mass, that oxygen, some of it might have come from the organic compound, but a lot of it came from the burning process where we put pure oxygen into the chamber. So, but all that carbon, since there's no other source of carbon, must have come from the organic compound. So by converting over 1.5 grams of CO2, first stage changes it to moles of CO2, then it's 1 to 1. So really this, even though it's nice to have this conversion factor for the units, you can see it's not really necessary times to get the right answer. And we end up with 0.409 grams of carbon. I'm going to redo that really quick. So this is the kind of thing that can happen as far as any kind of mistake, is where I'm just working too fast. But normally I'd catch it, because if you make any mistake along this line, you can come up with really absurd answers, and that generally tells you made a mistake. But if anything comes up where I've made some crucial error and I didn't notice it, I'll put that in as an addendum, or just start the video over. I hate to do it right at the end when I made one little tiny mistake. Okay, so 1 mole of water contains 2 moles of hydrogen. Here's where people make their mistake. It's 1 mole of water is 2 moles of hydrogen. Unlike here, it's 1 mole of CO2 is 1 mole of carbon. It's 1 to 1, but here it's 1 to 2. That's the big problem. And then 1 mole of hydrogen is 1 gram. And some students say, well, why can't we just skip this and put a 2 here? You can. Or, sometimes they'll see 1 mole of H2. I don't like doing that, and then this will be 1 mole of H2 is 2 grams of H2, because it's not hydrogen molecule. H2, when you do that means the hydrogen molecule, and that's not what's part of water. So I like to do it in moles of hydrogen atoms. But, if you've never thought about that, don't worry, but I just see it a lot with the students, and it's okay to do it if you're very careful. But I think it's better to do it by atoms rather than have some sort of theoretical molecule that makes up the water. And when we add these up, this is grams of carbon and hydrogen. Now look at the mass here. This is not 1 gram. If it came up to be 1 gram, then and since that's what we started with, we know there's no oxygen present. That's why we don't have to say that there's oxygen present. We'll figure it out. Well, obviously, if there's the carbon and hydrogen have been accounted for, and we still haven't gotten back to 1 gram, the rest must be oxygen, because that is what we have been told, is that there's only carbon, hydrogen, and possibly oxygen in this sample. So we end up with 1.0, whoops. And this would come out to be whoops, that's not right, is it? So, as I was saying, 0.40549 plus, yeah, I don't know, I got a little quick here, so 0.455. This is 0.4. I had a 0 there, so that didn't make sense. And what didn't make sense to me was that there was 95% of this molecule was oxygen. That just never happens. So that's how I knew I'd made a mistake. So 1. There we go. So now we know what we have, and we need, sorry about that. What is the mass percentages? Well, we know the mass, the total mass is 1 gram, so the mass percentage for carbon is equal to 0.409 divided by 1 gram times 100. So you can see this is going to be pretty easy. That 1 gram really helps out. Mass percentage of hydrogen is 0.0456 over 1. And the percentage for oxygen is this. So this is going to be nice and easy. This is going to be 40.9%, 4.56%, and 54.5%. And let's figure out what the total is. This should be approximately 100. And it comes out to be 99.96%. We've added these up, so we'd have to go just to the tenths place, even though this goes out to the hundredths, and that comes back to 100%. Because it does that, we know that these answers, these are correct. This is for carbon, hydrogen, and oxygen. Okay. And what do we have next here? Okay. So same thing. We're going to focus a little. That's my predetermined answer. I'll leave that on the side here. So we're going to do this one. I'll do it a little bit faster and just focus on it. So we have 3.87 grams of an organic compound, contains carbon, hydrogen, and possibly oxygen, is analyzed by the combustion method. So just the same problem we just did. We have this many grams of CO2, this many grams of H2O, one mole of CO2, 1 mole of carbon. 1 mole of carbon is 12 grams of carbon. 18 grams of water. It's 1 mole of water. So it should look exactly like what we just did. And that's nice to have a couple of them like this, so you know where you're headed. Even if the first one kind of threw you, you should have a better idea now. But boom, do them out. So 5.8 divided by 44 times 12, and I got 1.58 grams of carbon. I see it matches up. 1.58. For the water, that's just by chance that those two numbers happen to be the same. This comes up to be 0.176 grams of oxygen. Now, 3.87 grams minus 1.58 grams minus 0.176 grams. And that hydrogen is always going to give us that extra decimal place, and that's fine. We just keep track of our rounding. So this comes up to be 2.11 grams of oxygen. Now the mass percentages then is for carbon. We have 1.58 grams of carbon over 3.87 grams. for the total. So this is given here. I'll just do it as we go. Just make sure we have enough room. So this is 40.8%. For hydrogen, we have 0.176 grams over the total, 3.87 grams times 100%. Now, since we've done a lot of this, you might think we have, this is 4.55%. Now you might say, well, you could just take 40.8 plus 4.55, subtract it from 100. That's fine, but I like to do it all the way out because maybe I made a mistake somewhere along the line, and that won't tell you if you've made a mistake, because you're obviously those percentages are then going to add up exactly to 100%. It's better to do it out this way. So it's the oxygen 2.11 grams divided by 3.87. And I know I squeezed that in there, and that's why I always state what the numbers are that I'm working with. So even if you can't quite read it, you're going to hear me say that. So we have 40.8 plus 54.5 plus 4.55, and that comes up to be 99.9% total. So when we add these three up, we come up with 99.9%. Not exactly 100, but that's rounding errors. That's fine. That tells us we're right in the ballpark. Okay. Now, determining empirical formulas. Now, the empirical formulas, the reason that they're important, empirical means experimental. We get it from experiment. And that's what we find with this combustion data. We're going to see other problems in the next lecture, I think, or one of the next lectures, that you determine empirical formulas because that's all that you get from combustion data. You don't get the molecular formula. You only get the empirical formula. So we need to know what they are, even though it seems kind of ridiculous to do at first glance. It's like, why are we taking the true form and changing into something that it's not? Well, the empirical formula is the lowest ratio of whole numbers of the different elements. So here we have 2 and 6. Is there any whole number, any integer we can divide into both of them that will reduce them to integers? We could certainly divide both by 7, but that will give us a fraction. Well, if we divide both by 2, we end up with CH3. Now, that is not a real molecule, but it is the true lowest ratio. There are 2 carbons for every 6 hydrogens, but that's also 1 to 3. So it's 2 to 6, and we're just reducing it to 1 to 3. So that's the ratio. So, and the reason it's important because in the combustion data or combustion analysis problems and other forms of experiments in which you determine the ratios of these elements, they don't come out with the molecular formula ratios. They just come out in the lowest ratios of whole numbers, and that's the empirical formula. From there, then if we were to get this by combustion analysis, we then know that can't be the true molecule, but then we'd work from there and we'd figure out what it truly should be from another method. Okay, so we have this. Anything that we can do here? NaCO2. The next one is, there's 2 and 2, so we can reduce it to 1 and 1. Then we have 6 and 6. This is benzene, which reduces to CH. Notice these are the same. So we have 2 very different compounds. We have acetylene, which is a gas, has 2 carbons, benzene, which is a liquid with 6 carbons, but they have the same empirical formula. So even though that doesn't tell us as much information as the molecular formula, it does tell us a little bit about their structures. Here we have methane. It's 1 and 4, so its empirical formula is the same as its molecular formula. So you wouldn't say it doesn't have an empirical formula, you'd say that they are the same. And then this last one here, if we divide by 3, we get 1 here, and then we have 8/3. Divide by 8, that won't work. Divide by 2, divide by 4, divide by 5, 6, 7, 8. Anything above 8 will give us a fraction on this side. So there's no integer that we can put into both that will reduce them down to integers. So even though this is a very large empirical formula, that's what it is. The molecular formula is equal to the empirical formula.